Greetings, the Astro 30 here yet again with a brand new video for you. Now I've received a package in the post today which, box has been damaged. These are PCBs obviously, and you probably know by the title of this video what it's for, so I will open the box. It's always like Christmas, and there we go. And we'll have a take a look inside. One big box for a small amount of PCBs. Here we go. Well, at the moment you can't really see much except, well, my logo and shock hazard on the copper side of the PCB. We can't actually see the front of the PCB because it's hidden behind this cloth material which looks like it wasn't actually wrapped properly, or it's come adrift. Anyway, that's the board code there, W3831666ASZ28, and the name of the Gerber file was soft start Gerber zip. So let's open the plastic bag and we'll take one of the PCBs out and have a look. It's actually quite bigger than I thought it was going to be. So there we go, here is my toroidal transformer soft start circuit, and I don't need to tell anybody that this type of project is connected to the mains line voltage, so it is inherently dangerous. If you're following along at home, you do so at your own risk, but please adhere to electrical safety and do not come into any contact in any way of any part of this circuit whilst it's in operation. It can have the potential to kill you. Basically what I'm saying is, don't be a Billy, don't be silly and blow off your willy because you accidentally electrocuted yourself. No offence to anyone named Billy, by the way. So looking at the front of the board, it's nice. I did have plated through holes for the screws, but it just looks like a total waste of time because it's a single-sided board, and on the underside it's just a copper pad and there's no plating through hole. No, there isn't. So that was a complete waste of time to do that, but it does actually give some form of strain relief when you're actually cranking it down onto your metal. Now we'll notice immediately that we've got thick 5mm traces for the active and neutral lines. That is intentional. Down here is the link to where the idea for this circuit came from, and we will have a look in brief detail at that circuit in just a moment and explain what it is, how it basically works. Now it comes off of Rod Elliott's Sound Products website, of one of his articles, not one of his projects, but one of his articles. I don't think he will mind too much that I had a PCB made out of one of his articles. I don't think he'll even care, because it's an article, not a project that makes him money. And it's probably a circuit that he would probably not want to use himself, as he already has two versions of this available as purchasable PCBs. So anyway, let's have a quick look at the schematic of his website, of where I got this from, so we can see how it works and what it's actually supposed to do. So here's a quick look at the circuit on Rod Elliott's ESP page. It's a simple circuit that's all around the internet. The only change I made to it, well, I actually accidentally made another change I shouldn't have, but I've omitted this 1 amp fuse here because it is going to a normal line fuse elsewhere. Well, it should be anyway. The reason I did that was because if this fuse blows and these relay contacts go open, then all the current is going to be going through this resistor bank, and that'll eventually make these resistors overheat and fail. I'd rather it took out the main fuse first so that this circuit is dead, so is the transformer. As we can see, it uses a basic capacitive dropper here, formed via a 470 nanofarad X2 rated capacitor. That does not mean times 2, it means X2 rated. They're designed to work with 250 volt AC. It's stated throughout this article several times not to use polyester capacitors in its place for safety reasons. Also, this circuit must be used with double insulated wiring because these are inherently dangerous. So as we can see, this capacitor is now bypassed also by these two 470k resistors, which forms around about 935k. All that resistor's job is to prevent spikes from the line going across this capacitor when it's initially powered up. We've also got this 220 ohm 1 watt resistor on the neutral before the bridge rectifier over here. What this is here for is to isolate any noise that may be generated on this circuit going back onto the line. There are a few LED light globes, well, I think one particular brand of LED light globe that does not include a 220 ohm stopper resistor, for want of a better term, and it will generate quite a bit of noise on the line, including injecting it onto AM radio reception. I think it was John Audio Tech did a video on a particular LED light globe that did exhibit those effects because it was missing this resistor here, this stopper resistor, for want of a better term. It was either John Audio Tech or BigClive.com. I'm not 100% sure on that, but anyway. That then goes into a full bridge rectifier formed out of these 4 diodes. Now I'm using a button rectifier. It does the same job. And the timing aspect of this circuit is solely relied upon by this capacitor here, this 100 microfarad. Now on mine, I've made it 470 for whatever reason, I don't know. But this capacitor, in conjunction with this 1K4 relay coil, and it must be over 1K resistance for the relay coil, or the timing will not work. So you can't use like a 12 volt relay coil of say 180 ohm. It's not going to have the same timing effects because it's using the charge constant of this capacitor in conjunction with this relay coil to form basically a RC delay. That in conjunction together with this pulsing of what this capacitive dropper is doing. What the actual capacitive dropper here would drop the voltage down to, I don't know, probably 30 or 40 volts, something like that. But we're clamping that voltage down with this diode here, a 24 volt Zener, and that also provides a bit of back EMF protection from this relay coil when it de-energizes, so it's not going straight back into the diodes or the capacitor. I still do not know why I've put 470 there. Whatever. Anyway, the contacts of the relay, the normally open contacts, go across this resistor bank, which I'll get to in just a second. That connects from the active or the live coming in, and it goes through the resistor bank straight into the transformer's primary winding. So this acts as a ballast or current limiter when this circuit hasn't energized the relay yet, and as soon as the relay clicks in after about 90 to 100 milliseconds, then it effectively shorts this resistor bank out and allows all the current from the live to go straight into the transformer. Because if it didn't, then this resistor bank would overheat over time and eventually fail. Further up the page, this is what the resistor bank is made up of. 3 150 ohm resistors in parallel, which gives us a total of 50 ohm in the end, and 15 watts. So as we can see, the active comes in through the resistor bank out to the switched active, which goes to the transformer, and as soon as the relay contacts close, it shorts that resistor bank out, allowing the current to flow through directly to our load. And I'll put a link in the description to this article so you can read it thoroughly yourself. But I will remind you that this circuit is at mains potential when it's in operation. So if you don't know what you're doing, don't attempt this at home, because the propensity to come into contact with parts of the live circuitry whilst it's operating are quite high if you don't adhere to basic electrical safety. Anyway, let's get the thing built and see if it works. So that's the not so in-depth description of how this circuit works. And as I said, all it's really for is for the first few 100 milliseconds of power on is to reduce the inrush current experienced by a toroidal transformer. EL core type transformers aren't so bad, but the bigger the transformer, you do still get a fairly large influx of current going into it when it first magnetizes. So again, say for instance that broken Pioneer amplifier with a humongous power transformer in it could probably benefit from a soft start as well. However, it doesn't work, so it's not even going to be a remote possibility. Now, I don't have the parts yet to build this, but also, as this is connected to the mains voltage, I do not, under any circumstances, want this to blow a circuit breaker. So this will have to be put on hold until such time as I build, which will be featured on the channel, a dim bulb tester, which is a current limiting device with a light globe, incandescent light globe in series with the active, and it reduces the initial inrush current of circuitry. Plus it also prevents the issue that if this circuit board somehow had a short circuit in it, from blowing the line fuse or taking out a circuit breaker in your house, which is one thing you don't want to do. So as I say, this circuit will have to be put on hold until such time as I build the dim bulb tester or limiter. Anyway, but this will be built and tested before the end of the video. Okay, so I'm going to start assembly with what I have. Do not substitute values under any circumstances, or else, especially this capacitive dropper, will not work correctly and you'll be putting your line at risk. So I'm going to start with the small 470k resistors. Now it's single-sided, so I should not need to have the iron on there for too long. Just long enough to solder it like that. That's perfect. Okay, what I should install next is the spade terminals, because it's easier. Alright, they're soldered in. Next would be this 220 ohm 1 watt resistor. Just measuring it up so I know where to bend the leads. This needs to be mounted proud of the board like normal, as this is the, I want to call line suppressor resistor. It stops any noise being injected back onto the line. Alright, finally got it in there. Right, that should be far enough away from the board. I'm not going to take too much video of assembling this because, well, again, what is the point? I'm only just, you bastard, I'm only just bringing you tidbits along the way, because it's kind of unnecessary to film the whole process. I mean, it would be 15 minutes of me assembling a PCB. Yeah, that's real great content, Astro. Real great content. Never like when that happens either. There we go. Right, that's the resistor in, so I might as well install the electrolytic capacitor. I mean, I can get the diode and the bridge rectifier to get as close to the board and the other capacitor quite easily. So I might install this 470 microfarad 63 volt, which I bought the other day to test something else, and now I no longer need it. So I can use it for this. It's starting to look like something now. It's part the way assembled. I've run out of components. I need 5, 6, 7 more components and it's done. And yeah, really. Well, I'll go get those during the week this week, finish off the assembly, and then we'll come back and I'll show you the completed board. Right, why didn't anyone tell me that this capacitor was actually in backwards? I've just turned it around. This is what happens when you talk. I had this with a negative over here instead, which is the incorrect polarity. This would have gone boom as soon as I plugged it in, which would have made for great video, but this is the Astro's Electronics Lab, not Electro Boom. I don't really want capacitors going boom in my face. Anyway, that should be correct now. I always look at my PCBs after I've assembled them carefully to make sure that I've assembled everything right. In this case I didn't. which is a good practice to have. And being a single-sided PCB, this stuff is very forgiving and easy to unsolder components and turn them around, unlike plated through holes, which can be a real bastard to try and get the solder to clear out of. So you can either put the component in the correct way around or put a new one in. Anyhow, I'll move on to the rest of the components and we'll come back when it's completely assembled. Alright, I've been out to J-Car and I've got some parts for this circuit. I've got the diode, the 3 power resistors that I need, the relay, it's a 24 volt relay, and it should have a coil resistance, or DC coil resistance of around 900 ohms, somewhere there. I can verify that, but I want to make sure it fits in my footprint first. If it doesn't, with a problem. No, it fits fine. Okay, so I want to verify the DC resistance of that coil. We've got close to over a K, which is what we need because the circuit requires a relay with a DC coil resistance of at least a kiloohm. I think it was in the text something like 900 ohm was the minimum you could use. Otherwise the delay functionality of the circuit will not work. So you can't use like a 12 volt relay with a, say, 170 ohm coil or something like that because it just simply will not work. Right, so knowing that the relay is the right coil resistance, I'm not going to put that in yet because I want to test this circuit without the relay installed. But I am going to install the full bridge rectifier if I can. Now, I don't know how much heat this diode's going to experience, so I'm going to solder it so it's raised slightly up off the board. Just in case that starts to dissipate quite a bit of heat, you don't want it scorching the board. I'm going to measure the resistance across that input because it shouldn't be short-circuited because that's not how the circuit works. The other lead there. And we've got mega ohms, so yeah, that's going to be perfectly fine to connect up to the line without causing any issue like blowing circuit breakers, but I'm still going to put it through a dim bulb just to be 100% sure. So what I'm doing now is I'm injecting a DC voltage into the bridge rectifier and measuring across the Zener diode. Currently that capacitor is holding a charge, it is actually turned off. So I've got it hooked to my little bench power supply, which I'm going to have to fix the voltage sense wire on now because it's not working as effectively as it should. It's okay. Turn it on. And the meter says that we're at 9.7 volts and on the front panel meter, and the multimeter is saying it's less than that. But there is probably a loss through here anyway. So I'll crank the voltage up. We're at 15 on the supply, 15 on the meter, nearly 16 on the meter. But I mean, we are going to experience a drop through this bridge rectifier. So I'll crank it up right to the maximum of the supply, which is 19 volts. So indeed, the low powered circuitry is working correctly. Now if I back the voltage right off, it's going to take, it's at 6.5 volts on the supply, it's going to take a long time for that to bleed off. That is holding a charge for a considerably long time. It won't be in a second. There we go. Discharged. I do actually have a capacitor discharge tool for this, and I should really unpack it and make it a permanent fixture. Alright, so I've got my little soft start circuit hooked up to my dim bulb tester, now that I've got one, with a proper terminated line cord at the input here. That's come off of my variable power supply, so I've already done the crimping for that, so I might as well use the cable. It's plugged in. The switch is off. I've got the DC multimeter across this Zener diode. I'm going to measure what the voltage is. And I'm also going to be very quick to turn it off. So nothing went bang, the light didn't even flash. We've got 25 volt there. As we can see, as it's falling off slowly, it was up to the 24 volt mark. So I know that diode is doing something. So at least the capacitor, electrolytic capacitor, isn't going to go bang. So what I need to do now is discharge the circuit somehow. And the easy way for that is I'm going to use Danish Dart's little invention here, which is 2 multimeter probes connected across a 25 watt 3 ohm resistor. I'm just going to touch it across the diode, should discharge the capacitor. Boom, there we go. That circuit is now safe to handle. So what I need to do now is install this relay, and I have verified with a multimeter between this pin here and this outer pin that it is the normally open pin and not the other way around, because otherwise the circuit's not going to work the same. Alright, relay is soldered in, my dim bulb tester is still turned off. So now, turn it on. There we go. And there was a little bit of a delay turning off, but that's alright. So I'll count the frames that it took from when that switch turned on to when the relay clicked in, and I'll do it one more time just to verify and be very quiet. I'm going to assume that it's about 100 milliseconds. There'll be text in the bottom of the screen saying exactly how long it is. Alright, I've also got the resistors now soldered in, so we've got a total resistance here of 50 ohms, 15 watt roughly. I've got the multimeter hooked up into AC mode, and I've got it across the output. I just want to see if there's a voltage drop from 240 through these resistors until the relay clicks in. I mean, we may not see anything. I will hook it up to my toroidal transformer and power supply at the end, but for now, plug that in. No, we didn't see anything, but I can see that we've got the voltage coming out there, so that's good. So now I need to hook up the toroidal transformer and its power supply so there is an inrush, and we'll see what the difference is. If you remember from the video I did on building this dim bulb tester, what the toroidal transformer did, I'll turn it on. There we go. There you go, I just inserted a piece of video demonstrating that. So now we'll see what the difference is. Okay, got everything set up, and it's extremely safe. Don't do things like this at home unless you know 100% what you're doing. Remember, I'm still on my dim bulb tester, so if there's any problems here, it's just going to light the light globe up. Here we go. Now, point the camera at the globe and we'll see if there's a difference. Not much of one. There still will be inrush current, but it'll be a lot more limited, and the larger the transformer probably will exhibit exactly the same sort of effects here on the globe. So yes, but the theory does work. And there's no inrush that time because the capacitors are already charged on the power supply. So it does work. I haven't connected it directly to the line, but it doesn't need to be. We know that it works. It should be safe enough as long as there's an incoming fuse there to connect directly to the line. So the question you may ask yourself is, why did I go straight for a PCB without testing this on breadboard first? Well, the simple reason is we've got live mains running around this circuit here, and having it on a breadboard is extremely dangerous. Plus, breadboard is not really that well suited for that type of high voltage circuitry. I don't think these strips where all the components plug into are going to be suitable enough to handle any amounts of current like this. So yeah, that's why that's out. I could have built it up on Veriboard, but again, Veriboard, the lengths, the copper traces themselves aren't that thick. I mean, I could have shorted several of them together to make up one big, long current handling track, but It only cost me $5 to have that PCB made in American dollars and $8 in shipping in American dollars. About $26 Australian total, I believe it was, maybe less than that. Might have been $16. I don't know, I can't remember. But it was cheap. And the components, yeah, okay, there's $25 worth of components there. But it is, as far as I know, doing the job it's supposed to do, which is limit the inrush current of the transformer. So anyway, I'm going to leave this video here. If you found it interesting or you liked it, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and become a Patreon member for as little as $1 a month. I will make the project available on PCBWay if you wish to order a PCB for this. Please do, because that does help me out. I get discounts on my next PCBs that way. And anyway, this is the Astro 30 saying see ya. Have a great day. That dim bulb tester has paid for itself probably about 4 times now.